Next, we're moving on to talk about dispersion. Dispersion comes in three formats: range, interquartile range, and standard deviation. So range I've briefly spoken about before. Range is the difference between the biggest number in the dataset and the smallest number in the dataset. So at the top here, we've got my data. It's all spread out, it's random. I've rank ordered it here. 56 is the highest, 22 is the lowest. So now we get 56, we minus 22, and that equals 34. 34 is therefore our range. Like I said before, range is useful to show how large the data set is and where the values are between. However, it doesn't show where the majority of the data is. So here we've got 22, 25, 25, 26, 29. So that's 4 values before we even get to 30. Yet the range goes all the way up to 56. However, 56 is the only value above 50, as the next highest value is 46. But the range wouldn't show you this, it would just show that 34 is the range. So next we have the interquartile range. The interquartile range is a little bit more complicated. The interquartile range is the middle 50% of the data. So if we look at this strip here is 100% of the data. We're looking for the middle 50%. So to put it in a box plot, we've got 25% here and 25% here, and the 50% is in the box. So that is the interquartile range. So it's calculated the same way as the median values of data, and it's disregarded instead of position of the data. This is a problem due to not taking into account the values of the data. However, it shows where the middle 50% of the data lays. The interquartile range in a visual format may often be shown in a box plot like the one above. The box itself shows the interquartile range. So just like I said before, this box here, this is the interquartile range. This is 100% of the data between the whiskers. We've got 50 to 75 even to 100, sorry. And then we've got 25 to 0 here, and in the middle 50 is within the box. Same here, it's just at a lower level. Now, standard deviation. Standard deviation is related to the normal distribution curve, which I showed earlier on. Standard deviation is a number applied to show how far away from the mean the data falls. If there was a piece of data here, you would say that it is located plus 2 standard deviation from the mean. So, here we have an example of standard deviation. So, standard deviation is the 68% of the data. We split it in half. This would be your mean value. This would be a standard deviation either side. This is a standard deviation of 1. So, you would say that 68% of the data is in the standard deviation of 1 in this data set. Just another way to show where the spread of the data is. So we've got the range, which shows how big the spread of the data is. We've got the interquartile range, which shows you in the middle 50% of the data, and this shows where the data lays as well, but with standard deviation instead. Okay, moving on to the complicated bit, and going on to the statistical test. So we're going to start off with Pearson's rank order correlation coefficient test. So I'm going to go through this slowly. On the left-hand side, there's this really big complicated formula, but we're going to ignore that for a second, and we're going to look at the table on the right. So I've got 8 participants here. We've got their biceps and their triceps skin fold caliper scores. So we've got 5, 5, 5, 4, 4, 10, 15, 10, 6, 7, 3, 7, 7, 11, 9, 5. And then I've totaled them, so the total for biceps is 58 and the total for triceps is 55. We're then going to square all of the x values. The x values is our biceps. We're then going to square them. Obviously we can't square biceps, so that's blank. 5 squared is 25, that goes down to those 3. 4 squared is 16, that's those 2. 10 squared is 100, which is those ones. And 15 squared is 225. We do also square the total, which is 58 times 58, which is 532. So we then move on to the y value. Our y value is triceps. We do the same thing again. We total it at the bottom, which we found out was 55. And then we need to find out y squared, which is 6 times 6, which is 36, 7 times 7, which is 49, 3 times 3, which is 9, so on and so forth. And then we need to square the total as well, which is 419. So then we have x times y. So this is this value, the x value, times the y value in the same column. So participant 1 would be 5 times 6 equals 30. Participant 2 is 5 times 7 equals 35. This carries on all the way down. 5 times 3 is 15, 28, 28, 110, 135, 50, and total those up and you get 431. Right, now moving over to the complicated formula. So we have n. N is the number of participants. Number of participants is 8. Then we need to do the sum of x times y. Well, the sum of x times y is 431 minus the sum of x, which is 58, times the sum of y, which is 55. I put this into the formula, and that is this section above here, that top section there. I have then done this bit already and put it in here. This is square root of n, which is 8, the sum of x squared, which we worked out was 532, minus the sum of x, which is 58 squared, times the square root of n, which is 8, sum of y squared, which we found out was 419, minus the sum of y, 55 squared. That sounds really complicated, but I put it through the calculator, and we've got 29.6636905 times 18.08314132. They would be times together, and this would be done all in the calculator as well. So we do 8 times 431 minus 58 times 55. So you do this bit first. That got me 258 over 536.4127074, which left an R value of, when you divided 258 by that, 0.4809729457. Right, they're just big numbers at the moment. However, if we look at this table here, this was our R value that we just figured out, 0.48. We need to look at the degrees of freedom first, which is n minus 2. We had 8 participants, so that's 6 because n was 8. We need to look at the 0.05 column, which is this one here, all the way down. And we need to find 6, so 6 is there, which is 0.7067. This means that there is no significant difference as it is above 0.05. Right, we're moving on to the next test. This would be done with non-parametric data. This is the Spearman's rank order test. So we'd start off with participants. So here we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 participants, so n is 10. We then square n, which is 100. So we're looking at the skin fold, bicep and tricep again. So we've got the same data as before. And we rank them. So we've got the 2 4s here. They're the lowest in the data set. So they would be 1 and 2. But instead of writing out 2 4s, what we would do is we would classify them as 1 and 2. We'd add 1 and 2 together because that's where they are in the rank, first and second, which would get us 3. Then we'd divide it by 2 because that's how many there are, which would get 1.5, sorry. And that would be 1.5, 1 and 1.5, 2 in brackets. That's just how we write it. Here you can see we've got 3 5, so the same process applies. Instead of writing out 5 3 times, their positions 3, 4 and 5. So you'd add 3, 4 and 5 up, which gets you 9. And you divide that by 12, sorry, then you divide that by 3, which is how many there are, which gets you 4, and then that would become, so that's 4 brackets 3, 4 brackets 4, 4 brackets 5. So that just shows your position in the brackets. If there's only one of them, so for example we've got only 115, that is just where it is in the rank, so in this case that's 8. You don't have to put any brackets or any number before. Same process applies with the with the triceps with your y value, so this is your x and your y. And we can see that there were 7s, so we had to write that as 5, and we've got 5, 4, 5, 5, and 5, 6 in brackets. The rest of them were all plain sailing, and there was only one of them. We would then do the difference between the rank. So as you can see, the rank was 4 here, and the rank was 3 here, so that's 1. That's 4 and 5, so that's -1. 5 and 1, which is 3. And we continue going all the way down. You then add these all up, and in the end I got a sum of 6. And then we do the difference between the rank squared, so that's all of these values squared. So 1 squared is 1, -1 squared is 1, 3 squared is 9, etc. so forth, all the way down. We then sum that, which gave a sum score of 102. We're now going to input it into this formula in the top right. So we'd have 1 minus 6 times the sum of the difference squared, which is this bit, 102. So if you look at my first column on my first value here, we've got 6 times 102 squared, 6 times 102, sorry, over 10 times 100 minus 1, right? The reason we have that is because n is here, so our n is 10, and then bracket n squared, we figured out n squared, which is 100, and then minus 1. So you'd literally put it in just how it says, 10 bracket 100 minus 1. We'll then break it down into 1 minus 612, so we've calculated 6 times 102, and then we divide that by 990 because we've done 10 times 100 minus 1, so we do 100 minus 1, which is 99, and we times that by 10, which gave us 990. So that gave us a value of 0.381. Like before, we get a table which has the degrees of freedom and some other things on it, and we're looking at this 0.05 value here. So we got a score of 0.381. The degrees of freedom in this case were 8 because we had 10 participants. We have to minus 2 to calculate the degrees of freedom. We go along to the 0.05, and as you can see, we've got 0.74 there, right? 0.381 is smaller than 0.74. There is no significant difference. Moving on to the independent t-test. So we've got 10 participants here, and their sit and reach scores 1 and their sit and reach scores 2. So this is when it's parametric data and two separate groups do the same test. Sorry, my mind went blank. So what we had to do is we had to find the mean for both of these columns. So we've got 12 here and 14.9 here, and we do the and we find out the standard deviations. So what we do is we're going to input this into our formula here. So we've got the mean 1 minus the mean 2, so that's 12 minus 14.9. And then we've got to do this funky bit at the bottom, which is the square root of the standard deviation 1 over 10, and then plus the standard deviation 2 over 10 as well, and that's still square rooted. That gave me 169,607.974. I then figured out this formula and calculated it, and that gave me minus 0.000179. We'd move this over onto the table. The t-test score is here. This is what we just calculated. We've got to do the degrees of freedom, which is n plus n minus 2. So we had 10 participants. We do 10 plus 10 minus 2, which gets us 18. We go along to the 0.05 score, and then that's 2.101, and we can see that there's no significant difference in this case. The dependent t-test is calculated as follows. You look at your participants, and they've got 6, so n equals 6. We've got a pre-30-meter sprint and a post 30-meter sprint. So you can see all these scores, you'd sum them here, and the same again, you'd add all these up and sum them at the bottom. Then got the difference between the scores, and we'd sum the difference, and then we've got the difference squared, and we'd sum the difference squared. With the dependent t-test, you just follow the formula